Welcome to The Explainer. Today we're diving straight into the massive paradox of 2025. We're looking at a year where these just mind-bending scientific breakthroughs are crashing head-on into fracturing global systems. On one hand, we're literally mapping the universe and rewriting the fundamental laws of computing, but on the other hand, the very institutions funding this research are cracking under the intense pressure of an unprecedented military and geopolitical arms race.
So, think about this for a second. What actually happens when our greatest scientific leaps collide with our deepest global divides? We're going to look closely at how national security, defense priorities, and surging global military tensions are fundamentally reshaping the future of innovation. It's basically a high-stakes tug-of-war right now between humanity's collective intellect and strategic global rivalry.
13,000 times. Let that sink in. That is how much faster Google's Quantum Echoes algorithm ran compared to classical supercomputers when computing molecular structures. We aren't just taking baby steps anymore. We're making these exponential, paradigm-shifting leaps that jump straight from theoretical physics into practical engineering. And in a world where computing power dictates military dominance, advanced logistics, and the ability to completely shatter modern cybersecurity encryption, a 13,000-fold increase. It's not just an upgrade. It is an absolute game-changer for national defense.
All right, here's our roadmap for today. 1. A year of scientific marvels. 2. The quantum AI symbiosis. 3. Biomedicine and deep space. 4. The geopolitical tech divide. And finally, 5. Fixing the foundation.
Okay, let's jump right into Section 1, a year of scientific marvels.
In early 2025, it felt like practically every month delivered a massive historic milestone across wildly different fields. January brought us past a really sobering threshold, confirming 2024 as the hottest year on record, officially blowing past that 1.5 degrees Celsius mark. But, human ingenuity fired back almost immediately. By February, France's West Tokamak maintained plasma for 1,337 seconds. That absolutely shattered world records for nuclear fusion, proving clean energy is actually advancing incredibly fast. Then in March, we looked up and found 128 brand new moons orbiting Saturn. Fields that used to operate totally in silos are suddenly blending together to create this highly integrated, computationally driven ecosystem.
Moving on to Section 2, the quantum AI symbiosis. For decades, quantum developments were pretty much confined to university physics labs, right? While classical machine learning ran enterprise software. Well, not anymore. Classical machine learning is now actively stepping in to stabilize incredibly fragile quantum hardware, and in return, those quantum processors are accelerating neural network training. It's this unstoppable feedback loop, and frankly, it is the quiet engine driving the most intense military tech race of the 21st century. It's completely revolutionizing how global superpowers model threat scenarios, optimize their defense supply chains, and build out next-generation autonomous systems.
The pace of this escalation is just breathless. I mean, a Nobel Prize in physics was just awarded for macroscopic quantum mechanical tunneling. Over in big tech, Google's Willow chip hit 105 qubits, proving that adding qubits actually exponentially reduces errors. That cleared a massive historical hurdle critics swore would take us decades to figure out. But the real heavyweight here is the military application. DARPA is pouring funds into the US 2QC program, looking at all sorts of diverse architectures like topological and photonic qubits. Their end goal? Utility-scale quantum computing by 2033, specifically to secure a decisive national security and intelligence advantage.
That brings us to Section 3, Biomedicine and Deep Space.
We're engineering at both the extreme micro and macro scales now, and honestly, a lot of this heavily mirrors advancements in the defense sector. Take these new life-saving pacemakers. We've shrunk them down to just 3.5 millimeters. It's basically military-grade miniaturization applied directly to the human heart. They fit in a syringe and are designed to just biodegrade when they're no longer needed. Looking upwards, SpaceX's Fram-2 just launched the first crewed flight into a polar retrograde orbit. And what's super notable here is that the trajectory data for this civilian flight was tracked very closely by Space Force telemetry. It really shows exactly how intertwined civilian exploration and military space operations have become. Meanwhile, down in Chile, the Vera Rubin Observatory is opening its massive digital eyes to give us totally unprecedented views of distant galaxies.
It was high risk, high reward. We took the risk. That's a quote from physicist Tony Tyson, the guy who dreamt up the digital camera technology for that new Rubin Observatory over 30 years ago. And it perfectly captures the spirit of 2025's scientific community. Whether they're diving 9,000 meters into the ocean or spotting oxygen in infant galaxies 13.4 billion light-years away, they are constantly pushing into the unknown. But increasingly, they're having to do all of this while navigating incredibly complex global tensions just to secure funding and protect their data.
Which leads us directly into Section 4, the geopolitical tech divide. The harsh reality is, we are entering a rigidly dual-track world driven entirely by defense priorities. The United States is heavily leaning on strict export controls, trying to choke off access to the high-end chips you absolutely need to train military and frontier AI models, while really tightening its own domestic research security. In direct response to that, China has launched a staggering $140 billion quantum fund. They've gone all in on an open-source AI strategy, essentially weaponizing open information so they can innovate rapidly at the edge, completely sidestepping those hardware blockades.
And the financial divergence here is wild. The US is brute-forcing raw compute power with a massive $400 billion annual data center spend. Chinese cloud providers, on the other hand, are spending less than a tenth of that. Instead of fighting hardware with hardware, China is leveraging its massive manufacturing base to generate proprietary industrial and defense data right at the edge. So what we're witnessing is the cementing of two completely separate, mutually exclusive global technological and military ecosystems.
But here is the massive catch on the domestic front. While geopolitical rivals are racing ahead with blank checks for defense tech, the actual academic institutions supporting these scientists back home, they are crumbling. They are cracking under immense financial pressure, rapidly shifting political priorities, and an AI-congested academic publishing system that is literally burying genuine breakthroughs under an avalanche of noise.
71%. That is the devastating cut dealt to U.S. undergraduate STEM education programs this year alone. Combine that with a sudden, immediate freeze on National Institutes of Health grants, which impacts over $47.4 billion in biomedical research worldwide, and the reality is looking incredibly grim. The foundational pipelines of funding and talent are facing severe structural starvation at the exact moment we need them most to maintain our technological stability.
So how do we solve this? Let's get into Section 5, Fixing the Foundation.
To stabilize this golden age of discovery, policymakers actually have a pretty clear roadmap laid out. Step 1. We have to shift academic evaluation away from discounting publications and focus on real societal impact. Step 2. Transition from hyper-competitive individual grants to stable, mission-based institutional funding. Step 3. We absolutely need to overhaul and scale up peer review. And Step 4. We have to fiercely protect open science.
Breaking that down a bit, to fix the publishing crisis, we need innovative systems like distributed peer review, where applicants actually review each other's work to break those crazy administrative bottlenecks. We also need partial randomization, basically a lottery system for proposals that already pass strict quality thresholds. This ensures high-risk, interdisciplinary ideas that might struggle to get unanimous approval actually get funded. And crucially, we need open science corridors. We have to make sure perfectly valid national security and military concerns don't accidentally throttle humanity's collective intellect in vital, non-military domains like climate science and global health.
We have the tools right now to cure diseases, harness quantum mechanics, and map the farthest stars. But getting there? It requires a stable foundation and a level of global cooperation that actually transcends borders. So I'll leave you with this. Will 2025 be remembered as the year we mastered the universe or the year we permanently divided it? That is the ultimate question we have to answer. Thanks for joining me for this explainer, and keep exploring.